Hi everyone. So today we're going to be having a look at the application for our structure of the nucleus section, and we're going to be looking at the production of radioisotopes. So there are 4 outcomes related to this topic of radioisotopes, and we have to have a look at the nucleus and how it can be changed by the absorbing of different particles, and be able to explain using the equation down below about phosphorus 32 and how it's produced, and also looking at the uses for a particular isotope of phosphorus, and have a look at some more equations and look at the production of different isotopes and how they're used for hospitals. Alright, so with the application for our topic, we're looking at the production of radioisotopes. So a radioisotope is a particular element that has been stimulated or created in a man-made environment that is usually used for imaging for medical purposes. Now, radioactive isotopes, they can be produced by the absorption of different particles into a stable nucleus. So, for example, a neutron might be captured by a carbon-12 atom, and we have a new isotope, a carbon-13, is produced. So whenever this happens and we create the isotope that happens to be radioactive, which means it might undergo decay of some kind, it produces something that's unstable, we have something called a radioisotope. Alright, so one of the things we have to be able to do is talk about the production of a phosphorus 32 isotope. Now, this occurs in a nuclear fission reactor where there are really high numbers of free neutrons, and we'll talk more about reactors and fission reactors and different types of reactors in the last topic of this, as the last topic in this section. So inside the reactor, if we put some sulfur 32, which means 32, meaning that it has 32 as its mass number, so it's a combination of protons and neutrons. If we place that in the reactor, it starts to be bombarded by these neutrons, and what happens is one of those neutrons is captured by the nucleus or is absorbed by the nucleus, and that becomes unstable. So what happens is it produces a new atom of phosphorus 32. Now, sulfur 32 is a stable atom, whereas phosphorus 32 is radioactive, which means that it will undergo further decay to try and get back to its ground state. And if we have a look at the chemical reaction down here, what we have here is we have our, that's not a very good colour, a neutron being added to our sulfur, and what happens after the reaction is that we still have a total of 32 total nucleons, but we've gone down to 15 protons, which is why it's gone from sulfur to phosphorus, and in the process a hydrogen has been produced also. So we can see there that we had an additional neutron and a sulfur 32, and what we have been emitted is 1 extra proton or hydrogen nucleus. So everything is balanced there, and we've gone from a sulfur 32 to a phosphorus 32. Alright, so phosphorus 32 has several uses. Firstly, it's used as a tracer, and this is the most common application for it. And it's used to identify different types of cancers and malignant tumours, because cancerous cells have a tendency to actually accumulate more phosphate than normal cells. So the location of this phosphorus 32 can actually be traced from outside the body to identify the different locations of potential tumours. So because they absorb more of the phosphorus from that radioisotope, it can show up more easily in the images that you can take. And a more rare use of the phosphorus 32 is for radiotherapy for certain diseases. So polycythemia vera, sorry if my poor pronunciation of medical terms there, but it's basically the production of excess red blood cells, and what happens is that the radioactive phosphorus is absorbed by the bone marrow and gives a dose of radiation, which basically stops making the excess cells. So this is much less common than being used as a tracer. Alright, so following on from our magnetic and electric field section, when we talked about cyclotrons, cyclotrons actually pop up again in this section of the course. So protons and deuterons, it can be accelerated using a cyclotron, and what happens is then they're used to bombard a different type of substance to produce the radioactive isotopes. So for example, if we have oxygen as our target substance, we can accelerate using the cyclotron protons, and the oxygen can actually be used to produce a radioisotope of fluorine. And nitrogen can also be used, and we can bombard that with deuterons to produce oxygen-15, again a radioactive isotope. So both of these isotopes are used in something called positron emission tomography, and that is a particular type of medical imaging that we're actually going to be covering in our next topic. They have really short half-lives, both of these isotopes, so 122.2 seconds as a half-life for oxygen-15 and 109 minutes for fluorine. So they have to be produced as necessary, and it's why it's quite exciting that South Australia now has a fully operational cyclotron at the new SAMRI building, because before that all of our radioisotopes had to be flown in from the cyclotron in Melbourne. So you can imagine with a substance that has a really short half-life, things would have to be, the images would have to be taken for longer, and the people who are having the images done would be having larger doses to try and get the right resolution in their medical images.